In this video, we are going to explore the topic of acid-base buffers. Acid-base buffers are solutions that are designed to have a unique composition that allow them to resist changes in pH. So we're going to start off by describing this unique composition and the function of acid-base buffers, and then we'll dive into methods for calculating the pH of a buffer before and after the addition of an acid or a base. And then lastly, we're going to go more detailed into calculations and develop the so-called Henderson-Hasselbalch equation, which provides an efficient way for performing pH calculations involving buffer solutions. So to provide a little initial motivation for our discussion of acid-base buffers, I want to turn to a rather fascinating example of buffers in action. And this is a buffer that's in action in the human body. Specifically, we have this challenge in the human body where we have blood that, of course, carries nutrients and waste products to and from our cells, and is, of course, essential to maintaining life. Now, blood, the pH of blood specifically, must be maintained within a very specific tolerance. If you get dramatic fluctuations or even minor fluctuations in the pH of blood, that can be catastrophic, ultimately can lead to death, and certainly severe illness. And so the body has evolved to have a rather ingenious way of maintaining blood pH, interestingly, by using one of the byproducts of cellular respiration, mainly CO2. And so it turns out that human blood contains carbonic acid, which is the protonated form of bicarbonate anion, which is the result of CO2, right, that is being released again during the course of different metabolic processes that actually dissolves in the aqueous solution, that is the fluids in the body, and of course blood being one of them, to create a mixture of a weak acid, which is the carbonic acid, H2CO3, and the conjugate base. And it turns out that by having this mixture of a weak acid and conjugate base constantly present in the blood, that it helps us maintain the blood at a pH that's between 7.35 and 7.45. Now, as I mentioned, if we get deviations in the pH much outside of this range, this can quickly become fatal. Now, changes in blood pH above 7.8 or below 6.8 is kind of those cutoffs for fatal deviations in pH. And so again, extremely important from a physiological standpoint to maintain this pH. And so this mixture of carbonic acid and the bicarbonate anion conjugate base creates what we call a buffer. So a buffer is defined as a mixture that resists changes in pH. And so I want to take a minute now to explore specifically how this blood buffer system works. So if you consider the reaction involving the bicarbonate anion, shown here up top, and right here, where the bicarbonate anion can function as a base, because remember this is the conjugate base of bicarbonate. And so basically what you can see is that that base can grab protons and form our weak acid. So if you were to, say, add acid to that solution, right, in this case it could be the blood. So if acid or any sort of acidic compounds were added to the solution, then that additional concentration of hydronium ions could be absorbed or reacted with our conjugate base to form the weak acid. Okay, and so similarly, if we look at our carbonic acid, we could imagine that if we were to, say, add OH minus to this solution, right, specifically, adding a base, then that base could react, become protonated by our carbonic acid. And of course, we'd be using up or reducing the amount of hydroxide ions present. Right? And so what we want to do is we want to consider in turn, write out the chemistry for what's happening if you add an acid. And of course, write out what would happen if you were to add a base. All right, so at a chemical level here, if you add an acid, right, so we'll call this acid, we'll call it AH or some generic acid. So if we add an acid, AH, that acid will react with the conjugate base, and that equilibrium will shift to the right, forming more of the weak acid, H2CO3, and water. Right? Conversely, if you were to add a base, we'll call that some generic base BOH, so you get a base, essentially an OH minus, then that base can react with, and of course we'd have an E minus up here, that base can react with the carbonic acid, and you will then neutralize that base, and you'll have HCO3 minus left over, as well as whatever conjugate you have from the base that you added, right? So essentially, by having this mixture that has both an acid and the conjugate base, it provides these options for two pathways. One pathway to react with additional acid, and another pathway to react with additional base. And that is the crux of how a buffer system works. So to put this into a formal definition here, we're going to define a buffer solution as a mixture of a weak acid and its conjugate base, or a mixture of a weak base and its conjugate acid. Either way will work. And we'll use the term buffer solution or simply buffer interchangeably. And we see that buffer solutions resist the change in pH when small amounts of strong or weak, for that matter, acids or bases are added. And so to highlight this effect, what we're showing here is a image depicting a buffered and unbuffered solution comprised of pH 8.0. So we're using a color indicator to show that both of these solutions are initially at pH 8.0, and they're characterized by this yellow color. Now, if we add 1 milliliter, not too much given how much volume is here, but just 1 milliliter of a 0.01 molar HCl solution to both, we see that the unbuffered solution undergoes a dramatic shift in pH, causing a color change, whereas the buffered solution is able to absorb essentially that added HCl, and the pH does not change significantly. And so to examine this process in another way, what I want to do is start off by considering a situation where you have an equal concentration of some weak acid and its conjugate base. So we'll call HA the weak acid, A minus the conjugate base. Right? And so by showing these bars, we're representing the concentration here, right? By showing these bars of equal height, we're basically saying that a buffer solution containing equal concentrations of weak acid, HA, and the conjugate base A minus would have this sort of concentration profile. Now, if we were to add a strong acid, adding a strong acid is going to shift the equilibrium to the left because you're effectively adding a product here. And that's going to result in the formation of more HA. Okay, so shifting to the left. And so the net result of that shift will then be an increase in the HA concentration and a decrease in the A minus concentration. So thereby making the solution slightly more acidic. Similarly, if we were to add a strong base, well, addition of a strong base would shift the equilibrium to the right as the OH minus hydroxide is converted into A minus. And so the net result there will then be having, to have a net increase in the concentration of A minus, the conjugate base, and a slight decrease in the concentration of HA upon the addition of that base. So remembering here that the crux of this process working is that HA and A minus, what we're talking about is a weak acid. You cannot make a buffer using strong acids or bases. HA is a weak acid, and therefore A minus is the conjugate base of a weak acid, which is a conjugate base. As long as you have that mixture of weak acids or bases and their conjugate, you can get this sort of effect here that we're illustrating with those changes in concentration that make the increases or decreases in pH very minimal compared to what they would have been for an unbuffered solution. So let's go ahead and jump in and work on an example problem here. So in this example, we're going to calculate the pH of an acetate buffer that is a mixture of equal volumes of 0.25 molar acetic acid and 0.15 molar acetate. So acetic acid, in the presence of water in this aqueous solution, will dissociate to form hydronium ion and C2H3O8, so acetate anion. And so there's an equilibrium constant associated with this dissociation. And what we do when we're talking about an acid dissociating, losing a proton and forming the conjugate base, what we oftentimes use is a subscript A to denote that it's an equilibrium constant for an acid dissociation, right? And it turns out that that equilibrium constant for this acetic acid equilibria is 1.8 times 10 to the minus 5. All right, so we can use what we talked about in our previous unit or discussion of chemical equilibria to write out an explicit expression for that equilibrium constant using products over those reactants and write out that equilibrium constant value. Now, we can write out then an ICE table. Sorry about that. The equilibrium constant expression for the acetate acetic acid dissociation reaction is going to be written as follows, right? We have the hydronium ion concentration up top and the acetate ion concentration up top as well in a product, and then our initial reactant. And of course, as always, the liquid water does not show up in the expression. So to calculate the pH, we are given initial concentrations for acetic acid, initial concentrations for acetate, highlighted yellow and orange respectively. We can build up an ICE table with both those concentrations provided, and then we can run that calculation. Now, once you have those initial concentrations written in, we can finish off our ICE table. We're going to represent a change in that concentration. We've decided to just go ahead and put a minus X on the left-hand side, plus X on the product side. And then you'll come up with your equilibrium concentrations. The next step is then to use our Ka expression coupled with those equilibrium concentrations to build up an expression that pulls it all together. And we now have an expression for Ka in terms of our unknown variable X, representing that change from the initial conditions as we reach equilibrium. All right, now, if we were to assume a small value of X to simplify our work here, we can solve our equilibrium constant expression as follows and come up with the value of X that's on the order of 3 times 10 to the minus 5. And so 3 times 10 to the minus 5, that's going to be our value of X. That's going to be the H plus hydronium ion concentration. And so when we come up with this value for X, we always want to compare that value of X relative to those initial concentrations, 0.25, 0.15 in this case, and double check that our assumption was in fact valid. And of course, in this case, our double check shows us that yes, we're in good shape. That 10 to the negative 5 is very small relative to these initial concentrations. And finally, our last step here is to determine the pH from that hydronium ion concentration, which of course comes down to just taking that negative log of our value of x that we just solved for, and keeping in mind that we've got two sig figs here, so we're going to report 2 decimal places on our pH, giving us a pH of 4.52. All right, so here's an example of essentially doing a pH calculation for a buffer solution using our ice table approach. What I want to do in the next slide is give us essentially a shortcut method for determining pH for these buffer systems. And that shortcut method involves a so-called Henderson-Hasselbalch equation. So the method of using the Henderson-Hasselbalch equation is as follows, right? We are going to be provided with a quick and easy way to determine pH of a buffer solution when that small x approximation holds. And so the equation, Henderson-Hasselbalch equation, is this guy right here. pH equals pKa plus log of HA, A minus over HA. And so when you're looking at the Henderson-Hasselbalch equation, there's a number of pieces of information we need. Of course, pH is what we're trying to find. pKa is going to be a characteristic of the specific weak acid we are dealing with. And so pKa, just like pH is a minus log of the hydrogen ion concentration, pKa is the minus log of the equilibrium constant, Ka. And so Ka for a weak acid, you should find in a table or find a pK in the table and plug that in here. And then, of course, the concentrations, ratio of concentrations of the conjugate base, A minus, and that weak acid, HA, will be there in the denominator. And so equation 1 here, the Henderson-Hasselbalch equation, essentially boils down to what we just did with our ice table calculation using the small x approximation. Because if you look at some generic equilibrium between a weak acid, HA, and its conjugate base, and write out the Ka equilibrium constant expression, you could rearrange the equilibrium constant expression to solve for H plus, and then take the minus log of both sides to give us minus log of H plus, which is of course just pH, and then minus log of Ka times this ratio. Well, you could change this minus log of the Ka times this ratio into minus log of the Ka, which is just pKa, and then take plus log of the inverted ratio to give you the plus A minus over HA concentration. So a little bit of algebra there from what we already are very familiar with, writing out equilibrium constant expressions. So to see that in detail here, we're going to take our pH. We're going to break out that logarithm, minus log of the Ka, minus log of HA over A minus. Plug in our definition for pKa, flip this ratio, and get a positive sign there. All right, so to see how handy the Henderson-Hasselbalch equation can be, let's consider an example going back to our acetate buffer solution involving a 0.25 molar acetic acid and 0.15 molar sodium acetate. So in this equation, your first step is going to be to plug in the given values into the Henderson-Hasselbalch equation. So we're going to take pH equals pKa plus log of this ratio. We're going to plug in our given values, and then the log of 0.15, and then down here 0.25, and then we come up with a pH of 4.25. And so, of course, this matches with our previous approach, but again, you didn't have to build up an ice table. You didn't have to do all the associated algebra there. It's basically a one-step solution for these buffer problems. All right, and so with that, we're now ready to start talking about buffer solutions and their pH after we've added a certain amount of an acid or a base. So first up, let's consider an example where we have a solid piece of KOH. And remember, KOH here is a strong base. All right, so we have a strong base, so many moles, is added to a 1 liter buffer solution that has this 0.25 molar acetic acid and 0.15 molar sodium acetate. All right, once again, it's our same acetic acid solution. We have that same Ka value, and we want to figure out the pH of the resulting solution. All right, so the method for determining the pH after adding a strong acid or a base is really 2 steps. The first step is to use stoichiometry to determine the changes resulting from the addition of the strong acid or strong base. Strong acids and strong bases are nice because they will completely react. By definition, they are strong, they react completely. So we can assume that reaction goes to completion and then solve the resulting equilibrium problem with the adjusted initial concentrations after we fully reacted our strong acid or base. Okay, so to see that in action, let's focus in on step 1 first. All right, so we're going to use step 1, using stoichiometry to determine the changes resulting from the addition of an acid or base. So remember the composition of our buffer, same as our previous problem earlier in the lecture video, we have acetic acid dissociating here. Now we're adding, in highlighted in purple here, KOH, strong base. So we're effectively adding OH minus, and that OH minus will react with our acetic acid to form acetate anion. And again, because KOH is a strong base, this reaction is going to go to completion. Okay, so if this reaction is going to completion, and we look at our balanced chemical reaction equation, we see that there's actually a 1-to-1 molar ratio between all species in the reaction. We find that by adding 0.020 moles of OH minus, we will consume 0.02 moles of our acetate, and then we will produce 0.02 moles of acetate conjugate base. Okay, and so notice that we're still going to have a buffer solution, right? But we've changed the concentrations of our weak acid and conjugate base. And so these changed concentrations or new concentrations of weak acid and conjugate base are what we need to use in step 2 here to solve the equilibrium problem. So we're, again, we could use an ice table here to calculate pH, but an easier path is just to go directly to the Henderson-Hasselbalch equation and write out our expression. pH is minus log of the Ka. We know Ka for this acid, and then plus log of the base or the acid, so A minus over HA. And in this case, in the numerator here, we started off with 0.15 molar of our A minus, but now by adding this base, we've increased the concentration of our A minus to now 0.17 because we've added in that 0.02 moles of our strong base. Conversely, the weak acid concentration starting off at 0.25 is going to be reduced by the number of moles that have reacted with that strong base. And that gives us our ratio of concentrations and our final pH reading. So as you can see, this pH has not changed significantly through the addition of this strong base, which again is that hallmark of a buffer solution. And so to highlight that, I want to bring up, consider what would have been the pH if we had added just 0.02 moles of KOH to 1 liter of water, right? So no buffer present. Well, in that case, we'd come up with a concentration of 0.02 molar OH minus. The POH would then come to 1.69. So pH would be 14 minus 1.69 or 12.3. So 12.3 would be the pH without a buffer, 4.61 pH with a buffer. Excellent way of highlighting the effectiveness of a buffer solution in terms of mitigating changes to pH upon the addition of a base, strong base. And so you can imagine you do a similar calculation if, for example, you were to add a strong acid. Again, you would just assume that all of that strong acid completely reacted, come up with some new concentrations and use those concentrations in the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation, of course, only works when we're dealing with situations that the small x approximation holds, which again, will generally be the case for weak acids and weak bases, which are required for these buffer solutions. Now that we have a nice, efficient way of dealing with calculations involving buffer solutions, we're going to now turn our attention in the next video to our final topic, which will be the topic of acid-base titration reactions.